Today, we're diving into two of the hidden structures that make our digital world feel so incredibly fast: Heaps and HashMaps. This is all about the quest for efficiency. So, let's jump right in.
Okay, let me ask you something. How does your phone find one specific contact out of thousands, like instantly? You type a name, and bam, there it is. Is your phone just packed with raw power, or is there something a little more clever going on behind the scenes?
Well, that's the big secret, isn't it? It's not about brute force. It's all about smart organization. It's about choosing the perfect tool for the job, the right data structure, to arrange information in a way that makes finding it ridiculously fast.
All right, first up on our quest, let's talk about priorities. Think about it. Computers are always juggling a million things at once. So how do they decide what to do next? Well, the answer lies in this really cool structure called a heap. To really get this, just picture an emergency room. It's not like a regular line at the store where it's first come, first served, right? No, an ER uses triage. The person with the most critical injury gets seen first, no matter when they arrived. And that's the whole idea behind something called a priority queue. Importance always trumps the clock.
So how do we actually build this digital ER? We use a heap. Now, a heap is a special kind of tree-based structure, and it is designed to do one job and do it perfectly, making sure the most important, highest priority item is always sitting right at the very top, ready to go.
So here's the deal. A heap has one golden rule, and it's called the heap order property. In this case, we're saying a smaller number equals a higher priority. Now look closely. See how every item is smaller than the ones directly underneath it, what we call its children? That's the rule in action. And it's exactly why the number 4 is sitting proudly at the top. It's our most critical patient, and the heap guarantees it's always right there, easy to find.
Okay, but that's the real question, isn't it? What happens when a new patient comes in and they're even more critical? Do you have to reorganize the whole hospital? No way. The heap has this incredibly elegant way of putting everything back in its right place. It uses a process that sounds kind of fun, the up-heap bubble. The idea is simple. You just stick the new, super important item at the very end of the line in the first open spot. Then, it just bubbles its way up to the top through a series of really simple swaps until it finds its rightful home. Let's actually watch it happen. All right, here we go. A new emergency arrives, priority 2. This is the most critical one we've seen. To keep the tree structure nice and balanced, we just pop it into the first open slot at the bottom. But right now, for just a split second, our heap rule is broken. Uh-oh.
And now the magic begins. The heap looks at our new 2 and compares it to its parent, which is 20. Well, 2 is definitely a higher priority, so swap. Just like that, our new item has started its climb.
And it doesn't stop there. The process just repeats. The 2 is now compared to its new parent, 6. Still higher priority? You bet. So they swap again. It's literally bubbling up the tree, one level at a time.
Okay, here's the final boss. One last comparison, this time against the root 4. And one last swap. And there it is. Boom! Our new, highest priority item is exactly where it needs to be, right at the very top. The heap's perfect order is completely restored.
But here's the truly mind-blowing part, the speed. This whole bubbling process has what we call a time complexity of O log n. Now, what on earth does that mean? It means it is ridiculously fast. Let me put it this way. If your list of tasks grows from 1,000 to 1,000,000, that's 1,000 times bigger. The number of swaps you need to place a new item goes from maybe 10 to just 20. It barely even notices the difference. That is the incredible power of logarithmic time.
Okay, so heaps are fantastic for finding the most important thing. But what if you don't care about importance? What if you just need to find one specific thing, like looking up your friend's phone number? For that, we need a totally different kind of magic. We need hashing. And at the heart of this magic is something called a hash function. The best way to think about it is like a perfect librarian. You walk up and give them a name, say Alice Smith. And they don't go searching through the aisles. Nope. They do a quick calculation in their head and tell you instantly, oh, Alice Smith, that's in aisle 7, shelf 3, slot 5. No searching needed. It's instantaneous. So how does this magic trick actually work? It's basically a two-step process. First, the hash function takes your key, like a name, and turns it into this unique but possibly gigantic number. We call that the hash code. But we don't have billions of storage slots, so that's where step 2 comes in.
a compression function. It just uses some clever, simple math to take that huge number and map it to a specific slot that we actually have available in our system. Pretty smart, right?
But, as with all great magic tricks, there's a catch. This system isn't quite perfect. There's one little hiccup that can, throw a wrench in the gears.
And that problem is called a collision. It's what happens when the hash function takes two different items, say John Smith and Sandra D, and gives them the exact same storage address. It's bound to happen eventually, even with the best functions. So what do we do now?
Well, the solution is actually pretty simple, and I think it's beautiful. We use buckets. Instead of each storage slot holding just one thing, we let it hold a little list. So if two items get assigned to the same spot, no problem. We just add the second one to the list that's already there. It's kind of like having a coat rack with hooks. If one hook is taken, you just hang the next coat on the same hook. It keeps everything neat and tidy and solves the collision problem beautifully. Okay, so we've just met two incredibly powerful tools in our quest for speed. The heap, which is all about priority, and the hash map, which is all about instant access. And this, of course, leads us to the most important question of all. When to use which one? And this is really the key takeaway. You pull out the heap when your main job is to always know what the single most important item is. Think of that hospital ER, or your computer's task scheduler deciding which program gets to run next. But you grab the hash map when you need to find any specific item, like right now, just by knowing its name or its key. Think of your phone's contact list or looking up a word in a dictionary.
And that really is the ultimate lesson here, not just in programming, but in all kinds of problem solving. There's almost never a single best tool for everything. Real efficiency, true elegance, comes from deeply understanding the job you need to do and then picking the tool that was perfectly designed for that specific job.
Heaps and HashMaps are just two of these fundamental, invisible structures that are constantly working behind the scenes to make our technology feel seamless. They're always organizing, prioritizing, and fetching things for us in the blink of an eye. And it kind of makes you wonder, right? What other brilliant, invisible structures are out there, quietly shaping our digital world and making the impossible possible?